Okay, I'm going to look at this example using Analgesics to illustrate what happens when we do an analysis of variance. Now, first of all, analysis of variance is used to compare 3 or more group means. We have an example right here. We're told a pharmaceutical company tests 3 formulations of a pain relief medication for migraine headache sufferers. 12 volunteers who suffer from migraines were selected. We don't know how they were selected. However, once they were selected, 4 were randomly assigned to one of 3 different drug formulations. So the 12 people who were selected were randomly assigned to the 3 treatments. That's important. The subjects were instructed to take the drug during their next migraine headache, and after the headache started, or 30 minutes after the headache started, once the headache started, they had to take the medication, and 30 minutes later, they had to report on their level of pain on a scale of 1 to 10, with, it says, 1 being no pain and 10 being extreme pain. When you run an ANOVA, and I'm going to show you how to do this in Minitab in a separate video, because otherwise it's going to get really long, first thing you want to do is get a box plot so you can visually see what is going on. When you run an ANOVA, the null hypothesis is always that all your group means are equal versus at least one of them is different. When I look at these box plots, it would certainly appear that people who had drug A experienced a lower level of pain than people on B and C. It looks like A is the clear winner. Question might be to ourselves is there any difference between B and C? B looks a bit higher pain than C. Maybe C is a bit better. We don't know that yet. All right, now over here I have put in the means for each of these groups, and it certainly seems like for drug A the mean is only 3.25, which seems to be a fair bit smaller than what we get for B and C. Is there a difference from B and C? Who knows at this point. And I've also indicated here, because it's important when we do the calculations, you take all 12 data points, throw them in the one pot, and get the mean of all 12. That's your overall grand mean. Turns out to be 5.5. All right. Box plots are important for ANOVA. Number one, it allows you to see whether visually there's any differences in what you might expect from your analysis. The other thing is, as it turns out, the data in each of your groups has to be normally distributed. That one looks pretty normal and symmetric. These two here are a bit on the left skewed side. Whether or not that's enough to make them not normal, I don't think so. We could run, and we will run, Ryan Joyner on each one of them, but I think we're going to be fine on that. And the other thing is we only have 4 data points, and you really cannot prove normality with only 4, so that's kind of limited use. All right, the other thing that's important for us to have a look at is the spread in the boxes themselves. I want to know, is the overall spread from the max to the min roughly the same for all 3 groups? And yeah, they're not exactly all equal, but they don't look really different from each other. So I would think that I got kind of equal variability in my groups here. All right, the calculations are shown here. Now, keep in mind, I'm not expecting any of you to do these calculations by hand. Minitab's going to plug all this out for us, but we need to see what's going on. So when you do analysis of variance, you have to calculate 2 estimates of variance, one within and one between the groups. And if you think about the formula for variance, when you do variance, you have to take every data point, find out how much it deviates from the mean, so every x minus x bar, you square those differences, you sum them all together, and then you divide by n minus 1, and n minus 1 is the degrees of freedom. So to calculate variance, you need to calculate sum of squared deviations, find that value, and divide by degrees of freedom. So what I'm doing on this slide is, first of all, I'm finding all the sum of the squared deviations. To do the within variance first, you take each of your data points and you find out how much do they deviate from their group means. So here, all of them being subtracted by 3.25. My next set are all being subtracted by their group mean of 7.25, and finally this crowd being subtracted by 6.0. Take all those deviations and square them and sum them together and you will get 7.5. Alright, so that's given me part of the calculation for variability within my groups. Now, I need to also look at how much variability is there between my groups. And the way we do that is we look at the group means as kind of being individual data points. Take those group means and find out how much do they deviate by the overall grand average. And in this calculation, each of these, by the way, is being multiplied by 4. That's because these averages, that 3.25, came from 4 numbers. And the same thing here and here. All right, we do all of this, square the deviations, do the math, sum the mess, and we get 33.5. And then what we do is we add these two numbers together to give us a total of 41. All right, the next slide talks about the fundamental Anova equation, and it says if you take an individual data point and you find out how much does it deviate from the overall grand average, this y bar bar. All right, I've done that calculation down here. There's my 12 data points, and every single one of them is being subtracted from the overall grand average. I've squared them and summed them together and I get 41. Well, that's the sum of the SST and the SSE. They worked out to be 33.5 and 7.5. So the Anova equation says, basically, if you take a data point, you find out how much does it deviate from the overall grand average, square that, do it for every data point you have, and sum up the mess. That is the same as taking the individual group means, finding how much they deviate from the overall grand average, square that and sum it. That's your SST, sum square for treatments, plus every data point minus its own group mean, square it and sum it, which gets you SSE. So when you add these two things together, you get SS total. All right, if you were doing this by hand, which you won't be doing, but just so we can see how the calculations are done, you then take the sum squares, and the sum of square deviations then get divided by degrees of freedom. The formula for degrees of freedom is not the same in each case. When we are looking for variance between the treatments, the degrees of freedom will always be 1 less than the number of treatments you have. We have 3 treatments, so here I'm dividing by 2. And the number 16.75 represents a variance term. This is the variability between my groups. Then I take my sum square for random error. I divide by degrees of freedom, where that's defined as total number of data points minus the number of groups. And essentially you lose a degree of freedom for every group that you're looking at. We had 12 data points, 3 groups, so this gets divided by 9. And this number here tells me how much variability I have within my groups. And then these two numbers here get compared to each other. All right, here's my Anova table. We will see something more or less similar to this from Minitab, except Minitab will just show me the numbers in red. Okay, so we've got the source of the variability due to the treatments, due to random error, and there's the total. We calculate the degrees of freedom, and by the way, if I sum up these two, I will get the degrees of freedom, and the total number of degrees of freedom will always be 1 less than the total number of data points you have. We've calculated the sum squares. You total them together to get you 41. The 33.5 gets divided by its degrees of freedom to give me the 16.75. 7.5 gets divided by 9 to get me 0.83. And then I look at the ratio between these two values right here. That gets me my F statistic. So my F value is 20.1. Now, when the F value is large, as it is very large right here, it basically means that there is a significant difference in your groups. Minitab will calculate for us an associated p-value. Your textbook goes on about using the F distribution tables. I am not using F distribution tables. We are simply going to get Minitab, or Minitab will give us a p-value, and we'll have a look at that. And as usual, we're going to compare p to alpha. All right, here's the printout you get from Minitab, and I'm going to talk about that later when I get to Minitab, so let's move on. All right, so when we go to make a conclusion here, we ran this hypothesis. The p-value was 0. Is our p-value less than 0.05? Yes, which means we reject the null hypothesis, and we conclude that at least one of our groups is different. All right, but we're not finished yet. In order to figure out which group is different, we have to run something called a multiple comparison test. And I'm just going to scroll down through these notes here for a moment, ignoring all this business about the assumptions. All right, so now we have rejected the overall null hypothesis. We now want to run something called a Tukey's test. And it's not turkeys, it's Tukey's. Okay, so you can read through all of this. Essentially, when we do this in Minitab, Minitab gives us this printout right here, and it also gives us a graph. It's always helpful to look at the graph in conjunction with what you are seeing right here. When Minitab does this, it always prints the groups out, not in alphabetical order, but in order of decreasing group mean. So drug formulation B had the highest average pain level, followed by C, followed by A. All right, Minitab uses these letter codes right here. And it says here, means that do not share a letter are significantly different. Now that means that drug formulation A, which has a letter code B, yeah, no, that can be a bit confusing. This drug formulation here is significantly different than these two here, different from the B and the C. How come? Because this letter B is not being shared by either one of these. Both of these have a letter code A, which tells me, from a statistical point of view, that there is no significant difference in the pain level of people on drug B or on drug C. All right, so you can look at it from the point of view of the letter codes, and in conjunction you should also look at this graphic. And what this graphic does is it shows you 95% confidence intervals for the differences in the means. And it tells you over here what it's doing. It's taking group mean B minus group mean A. All the numbers in this interval are positive. And by the way, just have a look at this graphic now. I got a 0, and you got a green line right here going through 0. Everything to the left, of course, is negative. Everything to the right is positive. All right, this thing here, all the numbers in this interval are positive. The only way I can get a positive difference is if B gives me higher level of pain than A. So that means A is better than B. All right, same thing going on when I compare C to A. This is C minus A. All the numbers in this interval are positive. Only way that can happen is if C gives me a higher level of pain than A, so A is better. And down here, when it compares the mean of C to the mean of B, this interval contains 0. It goes through this green line, and if it does, it tells us that there is no significant difference in those groups. So what's my final conclusion here? Yes, there is a significant difference in these groups, and pain medication A gave me significantly lower pain level than drug formulations B and C, and there is no difference between B and C. All right, I'm finishing it up here, and I'm going to do another video to show you how we go about doing this in Minitab.